A very good morning to all of you, and good evening to Professor Sarbajit Banerjee. I warmly welcome to our special speaker, Professor Sarbajit Banerjee, on day 6 of Indo-US Webinar, and also welcome all the participants who are being with us on all the 6 days of this Indo-US Webinar and the lecture series. Professor Banerjee, in his last lecture, he gives the insight about the chemistry of the lithium ion batteries. And today he will speak over the beyond lithium ion chemistry. So today, Professor Banerjee will speak on the designing electrode architectures across length scales, some lessons learned from beyond lithium ion scale. I hope and I wish the lecture will be highly informative, meaningful, and full of knowledge as we have these previous lectures. So with these words, I request Professor Banerjee to please proceed with his special lecture. Thank you.
Thank you, Tokeer. Thank you, Dr. Ahmad. It is, again, thank you for to those of you that have joined us on a Sunday. Thank you for spending your weekend with us. And I hope that you're staying safe amidst all of the lockdowns. And yes, so I'm going to get into a little bit more detail about options for energy storage beyond lithium ion. As we have seen over the last few days, energy storage is a major bottleneck to the energy transition, and solving this problem is going to be critical to essentially the entire energy transition, right? So let me tell you a little bit about some other options beyond lithium ions. And again, I want to acknowledge my group and then all of my colleagues who have the collaborations that have helped us work beyond lithium ion chemistries, particularly David Prendergast's group at LBNL, again, Louis Piper's group currently at Warwick University, and Dr. Partha Mukherjee's group at Purdue University, and Dr. Raimundo Arroyave's group at Texas A&M. So we've seen the need for energy storage, and of course, the invention of the lithium-ion battery, I talked about this last time, was pivotal to the growth of consumer electronics. You know, starting with the Sony Walkman and the camcorders, cell phones, laptops. This was all enabled by having rechargeable lithium-ion batteries, but now, lithium-ion batteries are completely the dominant paradigm in the field of consumer electronics, but there's a lot of need now for much larger format applications, both for mobility applications, so in electric vehicles, electric buses, electric airplanes, and ships, as well as for large area storage at the grid level, right? And there's a lot to be done. And this is really, if there's one thing you take away from my lecture and the last lecture, it's that there's just an incredible amount of opportunity at this interface of electrochemistry and material science. And really, we need a lot of talent. I think there's going to be a lot of jobs in electrochemical manufacturing. So that, you know, for students in the audience, this is just an incredibly exciting time to be working on batteries and working on the theme of energy storage in general, you know, whether it be hydrogen or batteries. And we have to really go back to the basics in terms of thermodynamics and kinetics and understanding fundamental mechanisms. And that, you know, the other thing is that the lesson that I hope you will take away is that there is need for all sorts of expertise, right? So again, for some of the younger faculty, PhD scholars and postdocs addressing that are attending the seminar, you know, we need folks expertise in organic chemistry, inorganic chemistry, physical chemistry across the board, right? This is required. So let's think about some of the problems that are going on. I've shown this slide before. You know, the move towards solar energy and wind energy is at the heart of our energy transition, right? We're essentially making we made this huge sort of push towards solar and wind energy, but the challenge that we're facing is that 1/3 of this energy oftentimes is thrown away because we don't have a way to store this energy, right? So this is a real problem. And for greater penetration of wind and solar, as you've seen, as these become a bigger and bigger part of the grid, we're going to need some viable energy storage solutions, right? And so I talked about this briefly last time. Curtailment is a major problem. So in many parts of the world now, solar energy and wind energy during times where when the load drops, we actually have to turn it off and we don't use it anymore. Whereas if we had a viable means of storage, we could be saving that energy for peak times when we cannot meet the demands, right? So you can sort of see this here, over. Let me sort of pointer. So as the load here drops, we're having to cut solar production and wind production, and then as it sort of peaks here, we haven't really stored energy. So this is a challenge, and so storage is a really critical part to sort of avoid curtailment. And in many parts of the world, like in Japan, electric vehicles, so mobility and grid level storage are increasingly coupled. You can during times of low load, you can be charging up your electric vehicle and using it, and there's a lot of things that you can do to match load and demand. So part of the idea is we need energy storage at different scales, right? So we need sort of some energy storage for batteries, for laptops and cell phones, another level for electric mobility in cars, and then for grid level storage. And there's lots of different options. There's no one size fits all. Depending on the application, we're going to need a whole range of different energy storage technologies. So on the one hand, on the horizontal axis here, you have the storage capacity. How much energy can you store? And then on the vertical axis, you've got the discharge time. How much time can you sort of get this energy back as needed, right? So there's some options where the discharge time is very small. You can store relatively small amounts of energy in a flywheel, but you can get that energy back very quickly. Batteries are expanding greatly in this direction. There's now gigawatt projects across the board, including in California. And then the discharge time is still quite fast. And again, this is so batteries are extending both in this direction as well as in this direction. And then you've got hydrogen. Again, you can store huge amounts of energy in hydrogen. Relatively slow to release hydrogen to get the energy back, because you have to essentially combust hydrogen in a fuel cell. So you're sort of limited by that. But again, this is a very good option for storing large amounts of energy. Pumped hydropower is currently the dominant technology for large-scale power management. So again, you can store very large amounts of energy. But the problem with pumped hydropower, of course, it's very geography dependent. You have to be able to have some sort of a mountainous terrain where you pump the water up, and then you sort of release that water when it comes down, right? So lots of different options. We're going to have to take advantage across the board for all of these options. Okay, so there's a variety of different things to consider. And when we talk about energy storage, we need to consider about power and energy. We need to consider about safety, portability, capacity, retention. There's a broad range of options. And there's a broad palette of technologies that we have at our disposal that we have to further develop. So on the one hand, lithium-ion batteries is the dominant paradigm when it comes to your cell phone. Lots of, for just very standard applications in cars, we still use lead-acid batteries. Electric vehicles are now also increasingly lithium-ion battery. Relatively site-level grid management is happening using redox flow batteries, right? So we've got a number of different options. We've got, so the correct choice depends on what sort of power density you need, what sort of energy density you need, right? So how much energy are you looking to store? Like I showed you in the previous slide, how quickly do you need to get it back? So what are your power demands? Of course, safety, right? So what sort of conditions are present? Are you going to store the energy in? Especially for aerospace applications, for instance, safety can play a very vital role where you absolutely do not want to have any fires or such on board of a airplane or a space shuttle. Portability can be very important in some considerations, like mobile applications where you're moving. In the case of an electric vehicle, having lightweight portable batteries is pretty important. In the case of grid level storage, not so important, right? So you can have relatively large facilities if you're trying to do grid level application, and perhaps cost at that point becomes more important. Then capacity retention, right? How many cycles can you get out of this? Again, this becomes, people are generally seem to be reasonably okay with changing their cell phone every 2 years or 3 years, maybe even every year. But if it comes to large scale facilities at the grid level, you probably are going to be looking for at least 10 years, maybe 20 years of application, right? So this becomes a major issue, right? So just before we get on to beyond lithium, let's think about lithium ion batteries, how they work, and what are their advantages, what are their limitations. So when you use a lithium ion battery, what happens is the thermodynamically downhill, or really a spontaneous reaction where lithium ions move from the anode, which is typically graphite, into the cathode, right? So the cathode is reduced. The cobalt, for instance, in a lithium cobalt oxide system, the cobalt oxide is reduced and you form lithium cobalt oxide. The electrons flow from the anode into the cathode, and so oxidation happens at the anode again, reduction happens at the cathode, and the current flows in the opposite direction, right? And it flows through a load. This is how I'm using my laptop while I talk to you, or this is how you might be texting while you are on your cell phone using this charging of a lithium ion battery, right? When you plug your battery into the wall to charge it, you are essentially doing work. If you go back to the fundamental definition of energy, you're actually doing work, right? And the work you're doing is a thermodynamically uphill process. You're pushing the lithium ions into a non-spontaneous reaction. You're getting lithium ions to move from the cathode into the anode, right? So you're essentially oxidizing the lithium cobalt oxide back into cobalt oxide, and those electrons are flowing from here from the cathode into the anode. The current is again flowing in the opposite direction, right? So this is what is happening during the charging of a battery. So you're using the power from the wall to drive the thermodynamically unfavored or the thermodynamically uphill reaction. And so by doing the work, you are storing the battery in a state where the moment you unplug it, the thermodynamically downhill reaction becomes favorable, and then you can use that until such time that this reaction is no longer possible, and that at that point the battery has run its course. This is a two-dimensional plot of different materials that are used. So once again, the free energy, we talked about thermodynamics, is delta G is equal to negative n being the number of electrons, F, Faraday's constant, and E, the potential difference between the cathode and the anode, right? So the voltage of the battery is the difference in the half cell potentials of the cathode and the anode, right? So the cathode is, again, where reduction happens, and if you know, the anode is where oxidation happens. So, and then the number of transferred electrons. So the theoretical capacity of a battery is defined in terms of, this is a term I'm going to use quite often today. The theoretical capacity is defined in terms of the number of transferred electrons, Faraday's constant, divided by 3.6 times the molecular weight, right? And so we care about the power density of a battery, the cost, the runtime, the Coulombic efficiency, the safety, its cycle life, reversibility, how easily can it form dendrites. And now increasingly, we are starting to worry also about recyclability, right? So lots of different considerations when it comes to batteries. And we have to, again, this is a part of the message. There's no one size fits all. Depending on the application, we're going to have to use different combinations of these properties. It's unlikely that we will find one set of battery chemistries that will meet every one of these applications, right? So in a perfect world, we would do this. So this is not going to happen. So depending on the application, we are going to have to make some compromises, some trade-offs, and accept some sort of combination, right? So in certain cases where, for instance, the cycle life might be more important, we might sacrifice on power density, or where safety might be more important, we might sacrifice on voltage, right? So these are some important trade-offs we're going to have to make in terms of technology, which is why it's important also to have a great large diversity of options, right? So let's take a look at this two-dimensional plot a little bit more carefully. So on the vertical axis is the potential. So you've got all the cathode materials on the top. This is lithium cobalt oxide, which is the this is the lithium cobalt oxide, which is the common cathode for battery for lots of applications, including electric vehicles. And then you've got all of the anodes at the bottom, right? So the seminal work by John Goodenough and M. Stanley Whittingham that led to the Nobel Prize paired these intercalation compounds with lithium metal, but then very quickly people realized that lithium metal is going to be very difficult to use in batteries, primarily because of the safety issues. And I'm going to talk in a lot of detail about the challenges with lithium metal. But so instead, Sony in 1991, based on the work of a French group and several others, also came up with something that is a much more viable solution, which is graphite as an anode instead of lithium metal. Okay, so a couple of things I want to point out comparing lithium metal and graphite. Of course, so graphite is a compromise. It's just really not as good because by moving to graphite, we're losing a little bit of potential, right? So lithium metal is going to give us a much greater potential, but really we're massively losing out on the theoretical capacity, right? So theoretical capacity of graphite is about 372 milliamp hour per gram. It's about an order of magnitude lower than lithium metal, right? And so there's a lot of excitement, a lot of interest recently in trying to see how we can go back. Again, this has been tried before. It hasn't worked, and many technologies have sort of gone obsolete. But how can we go back in terms of rechargeable batteries to lithium metal and replace graphite with lithium metal so that we can unlock this massive capacity, or at least some fraction of this, which would still be much higher than graphite, right? So there's a lot of excitement here in terms of accessing lithium metal batteries. So from the anode side, a big push is towards not just lithium metal anodes, but in general towards the use of metal anodes, which have much higher theoretical capacities, energy densities, and you can sort of see the numbers here for lithium metal. I'm going to show you some numbers later in this talk for other kinds of metals as well, right? Now, on the cathode side, lots of research, about a couple of decades of research, have identified some interesting metals that have pushed this voltage up, okay, and that have pushed the capacity as high as possible. The idea of multi-electron redox on transition metal sides to unlock more capacity has become quite good. But again, there's a lot to be done. We are, only using a fraction of the theoretical capacities in principle to run these batteries. So this is a huge challenge. And another challenge that has really become over the last 5 or 6 years a major problem is the actual criticality of materials, right? The sustainability of the materials. And a lot of this comes from, the problems come from lithium and cobalt, which are really two mainstays of lithium-ion battery technologies at this point, right? So you know, and this is when you do science, oftentimes you don't think about the worldwide distribution of minerals, but as batteries become larger and larger in size, and the scale of battery production massively increases, this has become an increasingly bigger consideration to take into account. Okay, so over here you can sort of see I plotted here the abundance of different elements in the Earth's crust. Of course, most of the Earth's crust is made out of silicon and oxygen. And then if you look at the remainder here, lots of aluminum, calcium, iron, magnesium, sodium. But then if you look at cobalt and lithium, which are these two elements that we rely on so extensively in lithium-ion batteries, very, very low in abundance, right? So this is a real big problem for us that we have to really you know, worry about. And I think to think more deeply about how could you use much more abundant elements such as iron instead of cobalt, or even something like vanadium, which I'm very interested in personally. And then how you know, in cathodes, and then how do you go away from lithium to something more abundant like magnesium or calcium or zinc, right? So this becomes a really important thing. So this is a periodic table, except that the elements are arranged by the relative abundance, how much is present, and then the different legends here talk about what sorts of threats do we have in terms of, you know, what is it that is, which of these are sort of, you know, relatively low in abundance. So you have things like, you know, over here, helium, we've got some major challenges. There's a pretty serious threat for some of these elements, and then rising threat from increased use across here, and then everything in green is pretty good, right? So, and then the other thing is you've got certain elements that are highlighted that are from conflict zones. So a few things to keep in mind, again, beyond just the scientific considerations, what is the Earth abundance of the elements? How much of these different elements do we have present in the Earth's crust? What is the geographic diversity of these elements? In other words, where can you mine these elements? You know, and this is also given geopolitical considerations, especially as it pertains to rare earths. This has become a pretty substantial challenge. You know, if there's one or two countries that control the entire supply of a certain element, then that is not really desirable from a manufacturing perspective, because that is a major supply chain risk. And there are certain elements where, for instance, 90% of all the worldwide production is in one country. So if you think about incorporating that one element into different applications, you know, you might suddenly come across some sort of a situation where that element is no longer banned. And we're sort of seeing some of these geopolitical considerations at play when it comes to, you know, raw materials for making vaccines and such, right? Who controls the world supply of specific raw materials, right? So then the next consideration is accessibility, right? How easy is it to access a certain element from its ores, right? So in the case of something like iron, you know, we have very well-established mining technologies that allow us to take all sorts of different ores and process it and get iron out. In other applications, it might take as many as 20, 25 steps before you can extract the metal out, right? So this is a major concern, and also, of course, adds to the cost of the energy storage technology. So how accessible, how easy is it? So, for instance, part of this element is the idea of the quality of ores. What is the percentage? So there's lots of elements here, including lithium, for instance. And lithium is not just the fact that it's relatively less abundant, but also to the extent that it is present on this planet, a lot of the sources of lithium are quite diffuse. That means that lithium is present in relatively low concentrations in seawater, ocean water, geothermal vents and such. Relatively small deposits, mostly in Chile and Bolivia, where you've got large amounts of lithium, right? And then the resilience of supply chains have to again do with so if you're going to go from a mine to a processing facility into some sort of a place where you get high purity materials and then you extract that. There's a lot of different steps involved, and we're going to have to, what are the different vulnerabilities at each of these steps. So, as you can see here, we're in the midst of this massive increase in energy storage, and therefore we're going to see a big increase in the amount of different elements like lithium, cobalt, nickel, manganese in the next few years. And cobalt in particular is a situation that is quite concerning. Most of the cobalt that is used in batteries comes from the Congo, and in the Congo, there's a lot of child labor, there's a lot of conflict, and this has become a huge issue from an ethical perspective, from the perspective of how are people going to get hold of cobalt. And there's a major concern in lithium as well. Lots of concern about related to the environment, as well as political ideas, especially, for instance, in Bolivia, that has seen a fair bit of instability related to lithium supply, right? So, so thinking about the future of batteries, thinking beyond lithium ion, right? We're going to have to move beyond, just from resource criticality considerations. It'd be good to move beyond lithium, and thinking beyond these ideas altogether, right? So cobalt, these are numbers are slightly older, but the price of cobalt has spiked quite a bit. Graphite can also be quite expensive. Nickel prices have also greatly spiked, and all of these are really driven by battery technology. So, one of the ideas that I also have tried to convey in the last few lectures is that while we are in the midst of this transition to green energy, we're also in a pretty strange situation of needing many critical materials whose accessing these materials requires perhaps not so green processes, and we have to be very careful about this, right? Okay, so the chemistry of different cathodes is just again important to review. Okay, so again, a lot of iPhones still lithium cobalt oxide. There's an increasing push to substitute cobalt with all kinds of other elements so that we reduce our reliance on this expensive element. So there's now a very large push towards nickel, manganese, so NCA and NMC are chemistries that have been adopted very widely, and people have had a lot of success with reducing cobalt much below 33%, even, or much below 15%, almost to very small values, which helps with this cobalt problem, but again, doesn't entirely solve it, right? So part of the challenge, I talked about electric vehicles, and we talked two seminars, when I talked about the overall picture about energy in the world, of course, transportation is a huge place where we get, by burning gasoline, by burning petroleum, we're generating a lot of CO2, and moving to electric vehicles is very important. And we are in the midst of this shift. There's a lot of driving forces that are pushing us towards adopting electric cars, both in terms of policy as well as different auto manufacturers, announcing these major roadmaps. But the single largest roadblock is the price of lithium-ion batteries. So if you take a look at this, this is an interesting curve. So the good news, right here, is that the lithium battery price has fallen quite a bit, from almost $300 here per kilowatt hours to about 110 here in 2020. The bad news is that it's not falling quite as fast as people had expected it to fall, right? So this represents a challenge, and again, it is a major roadblock to the energy transition, especially to the adoption of electric vehicles. So we're going to have to, push this price further down so that we can get parity with petrol vehicles, right? Otherwise, we've got extremely expensive lithium-ion battery that contribute to large prices of electric vehicles and make them, incompatible with, passenger sort of vehicles across the country, across the world, especially in emerging economies. So thinking beyond lithium, again, there's a lot of options, and I'm going to discuss all of these in terms of metal anodes. Just to resolve some of the criticality issues with lithium, sodium sort of is somewhat of a drop-in replacement. There's certainly challenges to the chemistry of sodium, and you could move towards using a sodium electrode, which also has challenges, but perhaps those challenges might be less than that of lithium. Magnesium and calcium are perhaps two multivalent chemistries that have received a lot of attention. And I'm going to spend a little bit of time thinking about magnesium. One of the advantages of magnesium, of course, very directly obvious to you. Lithium is 1+, magnesium is 2+, so you might be able to double the capacity, accessible by going from 1+ to 2+, right? On the magnesium metal anode side, similarly, because you've got sort of a 2+ ion, you can access a very large theoretical capacity. And then the other idea is that we've struggled so much with trying to work with lithium metal anodes, and because of the large propensity for dendrite formation. Is it possible by moving to magnesium or perhaps calcium that we can actually use metal anodes and come close to realizing these theoretical capacities, but without these same challenges of dendrite formation? So this remains a great thing. So metal anodes, of course, magnesium, calcium, as I showed you in a couple of slides ago, much higher abundance, calcium here, magnesium here, sodium here, right? As compared to lithium, and then there's potentially safety, potentially higher energy density that you can access. The challenges is, of course, so magnesium is 2+, and calcium is 2+, and zinc is 2+, compared to lithium plus, but the diffusion of the ions through a lattice is much slower, right? Because you've got a 2+ ion that is trying to move through the lattice, and that's much heavier in terms of its atomic mass. So the kinetics of diffusion are slow. There's challenges further with developing good electrolytes that allow for ions to be readily desolvated. Again, breaking the bond between the lithium cation and an anion is relatively easy. At the interface, this becomes a lot more harder for divalent cations, and this is really responsible for relatively sparse available electrolytes. So before we think about these other more exotic chemistries, let's think about going beyond lithium ion. The two chemistries that have, the three chemistries that have perhaps attracted the most attention all involve lithium metal, right? And either lithium metal paired with conventional lithium intercalation compounds, and so that instead of having graphite, you've simply replaced lithium with lithium metal, or replacing the cathode with something like sulfur, or replacing the cathode with oxygen or air, and just doing reduction on this on sulfur and or oxygen. And you can see why, straight up, why this is such an attractive concept. Instead of cobalt oxide or manganese oxide or one of these expensive elements, if you can use sulfur, which is dirt cheap and it's a byproduct and it's so light, or if you can use oxygen on demand without even having a real cathode, these are two very attractive concepts for getting very high theoretical capacity. So again, for a lithium sulfur battery, the number is 2600 watt-hour per kilogram. For a lithium oxygen battery, the number is 3505 watt-hour per kilogram. right? So if you calculate for lithium metal, charge divided by mass, so Avogadro's number times charge 1.6 × 10⁻⁻⁻⁰ divided by the atomic mass of lithium, so you get the capacity to 3.86 × 10⁻³ million. So really much higher, over an order of magnitude higher as compared to graphite as a cathode, as an anode, right? Okay, so one idea here is that I've talked about and discussed, that a lot of folks are very excited about, is the idea of an all solid state battery, and that has to do with taking a lithium anode and a solid electrolyte and matching it with a composite cathode, and this eliminates the need for necessarily having a separator and having a large porous anode architecture. So you can essentially use a tin metal lithium foil and access the full capacity of lithium. So there's a lot of excitement, particularly in the electric vehicle space. There's a couple of startups that are now valued at hundreds of millions, even $1 billion valuations based on this. Although this technology there's some commercial prototypes available, but hasn't really reached prime time yet. So the challenges with this, and this is perhaps the most accessible technology because there's only one problem to solve, and that is the idea of using lithium metal anodes. The challenge with this is that, as I'll describe in the next few slides, lithium metal can be very difficult to plate reversibly. Plate and strip over hundreds of cycles. A second challenge here has to do with the reactivity of interfaces. Lithium is an incredibly reactive metal, and when you put it together with cathodes with a solid electrolyte, it's inevitably going to be a bunch of reactions, and there's going to be some sort of passivating film form. What is that nature of the film? Is it permeable to lithium? What is the sort of resistance that gets built up at that interface? And then in a solid electrolyte and using lithium, where lithium is a conversion electrode, right? So lithium is being is getting into the electrolyte and then depositing out. There's large volume changes involved. How do you maintain physical contact between the solid electrolyte and the cathode, or the solid electrolyte and the anode across hundreds of cycles across hundreds of cycles? And a lot of this is done by applying pressure that keeps the stack together, right? Okay. So we might have to mute some of the other folks on here. Okay, so let's think about what is happening in the system. Lithium metal, like I talked about, is extremely reactive. And so one of the things that happens at the anode, reaction, when you use lithium metal will pretty much react with almost everything, right? As you know, lithium metal is going to want to get. Okay, someone's not muted. Can you make them? Okay, so just 1 second maybe to.
Hi, Sarbajit. Disturbance from, I think, your side. Because all mics are.
Mics are muted? Okay.
Yeah, all mics are. There is some disturbance from maybe some other window is open on your side. Please check.
Let me just give me 1 second. It will
coordination number of sodium chloride is Q.
Listen this voice. Voice is coming.
Question number 2. The plane which show allowed reflection in both BCC and FCC lattice are 102, 111 and 110. BCC के लिए all even होना चाहिए।
बैकग्राउंड में जो आ रही है आवाज इसी की बात कर रहे हैं अभी थोड़ी सी।
क्या होनी चाहिए even।
बैकग्राउंड में कोई आवाज आ रही है?
नहीं है, ये नहीं है, ये हो सकता है। Question number 3. A solid cation AB has NaCl structure. एक solid cation है AB जिसमें NaCl like structure है. If the radius of the cation is 120 picometer, the minimum value of the radius of the anion will be.
So did you find out any the issue, sir?
अभी apparently तो किसी को mic का movement नहीं है, but what I am doing is I am making all panelist attendees and see in case if it changes anything.
NaCl shows Schottky defect and AgCl Frankel defect. Their electrical conductivity is due to NaCl में भाई हमारे पास Schottky defects हैं और AgCl में भाई हमारे पास Frankel defects हैं. Their electrical conductivity is mainly due to the lower coordination number, motion of electrons and not the motion of ions.
There is some other event.
NaCl shows Schottky defect and AgCl shows Frankel defect. Their electrical conductivity is mainly due to the motion of ions and not the motion of electrons.
Dr. Sab, how many of you are there probably? So what there seems to be some technical issue with system because this voice doesn't seem to be from the event itself. So what we can try is I can generate a new link, right? All participants are here. I am not suspecting any of the participant to be actually doing it. So what I'll do is I'll share a new event ID with you and you can share with the probably the group itself, right? And on that we join.
Crystal, the value of the interplanar space cubic crystal is
otherwise I need to open a case with Cisco and find this out. Why is this happening?
The cell constant is.
What do you suggest?
Okay, you're on mute.
You are mute.
whether all the attendees will be able to join that particular link that you are going to generate.
Otherwise we need to wait, and then I can find out from Cisco what is happening actually, because this does not seem to be from our side or from the attendee side.
We can
in our
Unmute.
the value of interplanar spacing for 4
नया लिंक जनरेट कर दीजिए, पर वो आज के लिए होना चाहिए सर।
constant is
आज ही के लिए क्या?
हाँ, अभी के लिए सर आप नया लिंक जनरेट कर दीजिए। उसमें क्या करूंगा, ये भी जो चैट बॉक्स है ना सर, चैट बॉक्स में
दे देंगे,
कर लेंगे सर।
इसमें देके यहाँ से सबको उधर लेके जाते हैं, and इसको चलते रहने देते हैं ताकि so that we can diagnose this issue actually.
हाँ।
या तो इसका मतलब सेल्फ कांस्टेंट का मतलब शायद ये होगा,
पर वो आवाज तो आती रहेगी सर।
हाँ, मैं वही कह रहा हूँ। नहीं वो जनरेट, अब दूसरी मीटिंग चल रही है, उसमें कोई इशू नहीं हो रहा एक्चुअली। This is for the first time I am experiencing this. So let this event continue. We will exit from here. देखते हैं अभी कैसे करते हैं। पहले मैं बना लेता हूँ एक, so that the time is not lost.
अच्छा, अगर हम इसी को रीस्टार्ट करें तो फिर भी प्रॉब्लम रहेगा
जी?
अगर हम इसी इवेंट को रीस्टार्ट करें, इसी लिंक को, मतलब सारे लोग लॉग ऑफ कर दें फिर रीस्टार्ट करें।
पहले एक बार मैं शेयर कर, क्योंकि
हाँ शेयर कर दीजिए सर। कंटिन्यू चल रही है।
Do you have WhatsApp group of all these participants?
नहीं सर, WhatsApp ग्रुप नहीं है
ना?
नहीं है।
हाँ, क्योंकि टाइम ऑलरेडी ओवर हो गया, तो रीस्टार्ट आई कैन ट्राई डूइंग दैट, बट एक बार एक स्टैंड बाय लिंक शेयर कर लेते हैं, ऐसा करते हैं।
बिल्कुल
स्टैंड बाय लिंक शेयर कर लेते हैं, उसके बाद इसको रीस्टार्ट करेंगे।
राइट,
नहीं होता तो स्टैंड बाय लिंक पे जाएंगे फिर। ठीक है
सर।
जस्ट अ कपल ऑफ मिनट्स।
Hello participants, there is some technical issue from the Cisco WebEx side, and we have faced this issue for the first time. So Dr. Nakvi is generating a new link that we will share in the chat box, and you please save that link with you, because actually there is no WhatsApp group, so that we can't actually able to send you that link. So we will log off from this meeting for this link, everyone, and then we will join on the same link, this one. If we are able to get everything fine and there is no voices coming, then we will continue on this link only. Otherwise, if some problem is there, then we will actually move another link that Dr. is generating.
Then the value of D4240.
Thank you. Meanwhile, you can have the break if you want.
Under root 2 per square plus 4 per square. With root of 1 per square plus 2 per square plus 3 per square. 4 plus 16.
This is a good suggestion from the participant side, that please restart the session. Yes, we will start the session from only this link. But before that, Dr. Nakvi is generating the new link. If some problem is there, then we will come on that another link. Amir, what you do, you actually, if when the link is generated, you share that link also by email.
फिर साहब देखिए, डे 6 का लिंक एक तो ऑल्टरनेट ये मैंने दे दिया अभी। पार्टिसिपेंट्स में प्लीज टेक नोट ऑफ दिस। We will start this after 15 minutes, 11:15, or in the meantime we will disconnect from this meeting and re-enter it.
Okay, sir.
Fine.
Participants may please take note of this, right? Just copy paste this.
ठीक है सर। ये जरा भी Hamid.
So we'll log off now. Yeah.
Yeah, so I am disconnecting the meeting. Tokeer sir, today, has everyone taken a note of this? Maybe I can give half a minute more.
Yeah. Everyone, please note down this link, copy this link. It is in the chat box. It is in the chat box, and it is also sent by Amir by email. And you can log off this meeting, and after 5 minutes, we log on the same link that on which we are present over here. And if this link is not working, then this new generated link we will reassemble at 11:15. So that link will start at 11:15. So please, everyone, please log off and try to join the meeting from the same link that we have right now after 5 minutes. And if the same problem is still exists, then the new link will start from 11:15. Okay. ठीक है सर?
Okay.
तो अभी हम सब लोग लॉग ऑफ करके